All right, let's catch up to where we're up to, so we know what we're trying to achieve. Okay, so let's have a quick look on the board and see what we're up to. We've done the ultrasound stuff. We did X-rays, and I left you with the pages to read on CT scan while I was away, so you're supposed to know about that. And then I asked you to look at this endoscope pages. Yep. I will. There is stuff on Google, but you guys, I haven't got a lot of Moodle yet. I'll finish uploading all that, but let's quickly go through endoscopes today. I'll quickly do. I also left you nuclear medicines. We'll try and outline that very quickly for you as well, because there's stuff you're supposed to have done. And what I wanted to do today was I wanted to get you through PET and MRI. And then once we've done that, that means we're in a position then to give you time to revise. Yeah. Yep.
He's in, what does he do? It's not radiography, it's not radiology, it's new medicine.
Yes, he's in nuclear medicine. He's in nuclear medicine.
Down at Tasmania.
All right, so let's quickly go through and have a look at some of the things.
And the other reason why I know that is because my sister, she's like doing something else to do with curing diseases with radioisotopes. That's as far as I understand it. I don't know what it's called. All I know is that there's radioisotopes and she's curing diseases. She's up in Wollongong. She's in a lab. And she's doing a doctorate, so I might call it a doctor.
Okay, so guys, the point is I'm going to use the fastest and probably worst way of getting through information, which is to talk at you and to show the PowerPoint. And I understand that this, for a lot of people, is not the preferred way to go, but that's okay. My aim is purely to cover content with you very quickly. So let's have a look at the nuclear medicine first up. I will get you to write some notes as we go. I'll turn the sound down because I don't need that.
No, I think it was,
All right. So what we see is that we've got a slide here. Some of this will be useful, some of it won't be, because it was actually made for elsewhere. We'll go through. The radio or nuclear medicine can be used either therapeutically or diagnostically. We look mostly at the diagnostic use. And it involves use of these things called radiopharmaceuticals, okay, which can be broken into two halves. The word radio, of course, meaning radioactive, and pharmaceutical meaning medicine, very briefly. So the pharmaceutical is just a drug, and it's purely designed to carry the nuclear source to the site you want it to be, want to monitor, right? So there are various types of drugs which are actively taken up by various organs of the body. The brain, for example, very actively takes up a type of glucose. So you choose a pharmaceutical to carry the radioactive material to the part of the body you want.
Can they give you the pharmaceutical, do they give you immune system depressants? Or?
No, no. not normally. And then you need the nuclide, which emits the radiation for detection, and that needs certain properties for it to work properly. And I'll just wait for a second while Riley rapidly.
So, is this like the sort of treatment where it's like...
Careful, what word did you just use there, which was the incorrect one?
treatment?
Yeah, it's for diagnostics. Yeah. All right. And of course, you need to be able to bond the radioactive nuclide into the pharmaceutical. Right. Now, you really need to, you don't need to write all this down, but you really need your pharmaceutical to only go to the place of interest. So you have a target organ. It's not very good if you have it go all through the body. Okay, so you need to choose it carefully.
Do they always use radiopharmaceuticals to like do diagnostics? Like,
No.
is that the stuff where they always like inject it? Is there other stuff?
No, they use all sorts of things. Depends which system or technique they're using. Okay, one of the main things you don't want is you don't want the pharmaceutical used to do things to the patient. It might make them feel sick. So it can happen, but you don't really want your patient to have side effects from whatever pharmaceutical you're using. So you try and make it something the body naturally uses. And the other thing is it doesn't have to be a pharmaceutical that is taken up. It can be something that causes another body reaction, which it grabs onto. So it talks there about the antigen or antibody reactions, and it can actually be picked up by antibodies and taken to various places. But you have to make sure the pharmaceutical ends up where you want it. That's the broad message. Okay. In terms of the nuclide you use, this is really important. This is stuff you need to know. It needs to have a good half-life. The half-life can't be in the order of minutes, and it can't be the order of days. It has to be in the order of hours. The reason is, one, it needs time to get to where it's going, right? So it needs to get into this. So you need to actually get it from ingestion to where it's meant to go. That's going to take a little while to happen because the body doesn't instantaneously do things, okay? Second thing is that it is a gamma emitter. Now, alpha emitters, you know what alpha is? Alpha radiation. Why is it no good for diagnostics? Can't get through, yeah. It's generating all this radiation and it can't get through the organ to get out, so you can't detect it. What about beta? Beta is highly ionising, and it possibly could, but it may not. It may be absorbed, but it also could come through. But the other thing about beta is being highly ionising. You really don't want that belting around your body too much. It could damage your DNA and do other things. Possibly, yep. Now, gamma sources, you can have low energy gamma, but it needs to be high enough for it to be easily detected. So they use sort of 50 to 500 kilo electron volts. Okay. The Optimum says they're 150 kilo electron volts. And that they will come through the body, that's good, but you don't want them there for days, because otherwise they do what beta radiation does, which is to damage your body. So your optimum is about that 6-hour range. And it needs to be suitable for incorporating the pharmaceutical. It's no good having a really good source that you can't actually combine with anything. And of course the other thing for struggling hospital systems is you want to be cheap. Now, can anyone tell me what the main nuclear source is they use in nuclear medicine? It's a good guess, but it's actually, that's more for treatment. Technetium-99m is used in about 90% of all cases. We'll look at it briefly, but very, very, very briefly. It's a gamma ray source. It's low energy, reasonably low energy. It's in that band of about the 150 kilo electron volts. Has a half-life of 6.2 hours or roundabouts, which means if you put in 100 grams of it in 6 hours' time, 50 grams of that will have converted to a new type of element, and only 50 will remain as technetium.
Oh yeah, but if it has like, do you ever fully get rid of it? If it...
Oh, that's like if a ball bounces half its height every bounce, does it stop bouncing?
So yeah,
it does practically.
So that means that that is also radioactive, doesn't it? because lead is a byproduct or something.
Not necessarily. What you will get to a stable, you will get to a stable state eventually when you go through your what's called your, what is it called? I've forgotten. Your decay chain. You actually get to a point where it comes to a stable element. Most lead is stable. Okay, let's move on. Quick. So you can copy off the next one. Right. As I was saying, these are the commonly used radionuclides. You don't have to know anything about them except. So you have technetium, 99M, indium, 111, iodine, 123, which is used for glandular uptake, including thyroids. There's.
So what do they go to from days to hours?
Which ones?
Oh yeah, 8 days.
It just depends upon which radioactive element you're using and why. Some of them are good for certain reasons, but you really would prefer not to be having the iodine 131 because it's in your body for it's got a half-life of 8 days. Yeah, you'd prefer to stick away from that. Yep.
You wait for someone, are you giving off radiation to them?
What do you mean, sorry? You're given.
When you have the radioisotope in you, do you give off radiation to other people? Like,
Yeah, you'd be radiating into people. Then here around. You'd set off scanners around as you walk around, all that sort of stuff. Okay, radiopharmaceutical kits. These, this is just saying that in the hospital they get a kit and they extract the radionuclide. So on the video I showed you, I'm pretty sure I showed you the nuclear medicine one, with Pinky, what's her name? Pinky Robson or whatever her name is, carrying the technetium generator. I'm getting blank looks. I have to put on that little QR code. You have to read it. So what they do is they, for British museums, hospitals, they fly in from Canada because they don't have their own reactor that makes these things, a box, and inside of it is molybdenum-99. And the molybdenum over days reacts and becomes technetium-99M, which is what they pull out to use in the medicine. It lasts for about a week. Okay, so they just simply, the hospital just gets a box and they just use that. Okay. This talks about things which you really don't need to know about, this next few. This one is important. So what they're saying essentially is you have the pharmaceutical either injected or ingested or whatever pathway you take. And as Marnie was asking, you become radioactive for a while, or the elements inside you are radioactive, so you're emitting gamma rays, and they can detect them with the gamma camera, which is then put up as an image. There are some issues and difficulties with this, however. So gamma rays, as you know, are high energy electromagnetic radiation. They can be scattered and they can be absorbed. What are they absorbed by? Lead. How much lead do you need?
Not that much.
Pretty thick, yeah. In the order of centimetres. And we don't have technology that focuses them, which makes it difficult. So this is the gamma camera. And this is what you do need to know. The top of it is what's called a collimator. It's essentially a big block of lead with holes in it, which allows the gamma rays through. Now that's important because it means only the gamma rays coming at about 90 degrees can go through it, right? It means that all the background radiation ones can't get through. And also, if it emits from here, out of me, you don't want the gamma radiation that goes that way to be picked up by the camera. You only want the radiation straight above the site so you can actually monitor that part of your body. So the collimator is very, very important. Underneath is the salt crystal or the scintillator, and that essentially absorbs the gamma radiation and gives off light. Sodium iodide, which is a scintillating crystal. So what that means is when the gamma ray hits it, gives off light. Underneath it are the photomultiplier tubes Photomultiplier tubes are very much like the thing in your phone, which picks up the light to make your camera work. And then underneath is the circuitry which picks up the flashes of light and makes an image out of them so you can see what's going on. Yep.
So when cameras in the megapixels, that would mean that there's a lot of photomultiplier tubes or something like that?
Well, it's a little bit different. The camera, in the camera, they use what's called charge coupled devices, which are similar to photomultiplier tubes in that they pick up the light and they create a voltage. So they do the same job. But for a megapixel camera, yeah, there's a million CCDs sitting in there underneath it.
That salt crystal, is that setting like that?
Yes, that's what I said. No, I notice you're talking, which makes it hard to hear. Just the basic camera, very easy. You only have to be able to sketch it. You don't have to make it look really pretty like that. I will. Very rough. That's excellent. That's what you want. I can print this off, guys, if you want, rather than let you.
I want to write down the labels. Just be sure I go.
Go previous. Yeah, I can do that. Collimator or Collimator. Collimator. Scintillating crystal. Yep. The PMTs, photomultiplier tubes. And then you just need electrical circuitry. No, it's all you need to know is makes an image. I mean, even that diagram's pretty simplified. See how quick Brad can write. No, I will. I'll print off the relevant little pages, I suppose. I'll click the button. Let's see when I release it. Send Riley mad. See if you can remember it. How your memory's going. Okay. The very last one was under the photomultiplier tube. Just put output circuitry image. Okay. If you talk about light, you have a glass lens, can focus it. That's what this picture shows. Right? So you get complex rays coming out, and it will focus it and make an image. That's not a problem. Gamma radiation, we don't have any way of doing it. So what we do is we take the radiation which comes at 90 degrees, it goes through the collimator and it plots a point there. And then from the base, it will go through a hole and it will plot a point there. So we can't focus it, is what it's saying.
So, sir, like drawing something like that, if it said to draw that in HSE, which would be very...
That's good enough. That's more than good enough. The thing about it...
through like 2 discs, a whole bunch of circles and wiry things going...
That's, yeah, you don't need very complex. Okay, this is just showing how the gamma radiation will have a peak of energy through the collimator in line with the source. Now the thing is that the collimator, no, but what you do need, what doesn't hurt to understand is that the size of the holes and the width between the holes have a lot to do with how well, in the collimator, how well you can get an image. So if you increase the depth of the D, so the deeper the collimator is, the better the resolution is going to be. The smaller the holes are, the better the resolution. Now, resolution is like you're talking about pixels. Imagine if it's when a 5 kilobyte camera and a 50 megabyte camera. Right? I could take a picture of a 5 kilobyte camera and you get a blurry outline of maybe a tree, and you'll know it's a tree, but you won't get any detail. 50 megabyte, you'll be able to see the eyes of the possum poking out the hole in the middle of the trunk, right? So resolution is how well you can see the differences in things.
Hey, sir,
yep.
Is the
Collimator, just a lead plate with holes in it.
Yeah, so it's essentially like a sieve.
Yeah, essentially. Exactly. Now, the other thing you notice is that resolution, guys, greatly improves with closeness. So in the movie, what you'll see is they have a gamma camera and a fellow's having his forehead looked at, and basically the camera's just about shoved through his head, because the closer it is, the better resolution you get. And that's a picture trying to show how resolution improves. Now, The problem is, too, sensitivity improves. That's your ability to pick up the source. Improves the larger hole size and a thinner collimator.
So basically, the higher resolution you want to make the pulse small, but also
But then you can't pick up as many photons, so your image will be very dull.
so you can efficient more longer.
Or exposure, or you need to work out your equipment so you have a compromise between the two.
Well, sort of like graduated.
Well, no, you just simply got to work it out. What is going to be the optimum compromise between resolution and intensity? Okay, the scintillation crystal. All this says is gamma ray hits the crystal, light comes out. Well, remember you have the collimator, then you have a scintillation crystal underneath it, the sodium iodide, and so when you no. What you're actually getting is you're getting excitement of electrons which just give off light. It's actually due to what's called Compton scattering, but you don't need to know that stuff. You don't need to know that. It's light. Okay. There's a couple of types of ways you can image. You can do static, which is just let it accumulate, switch on the camera, see what's there. Now, for example, if you've got a non-functioning kidney, you leave it for a non-functioning kidney. 20 kidneys are dead. One kidney will take up nuclear medicine, one won't. So when you take a picture, you'll only see one kidney. That's a static scan. You can also do the whole body scanning. I'll show you one of those a bit later. Or you can do what's called dynamic imaging, which is where you take a series of them and you see how it accumulates and then disappears.
Oh yeah, there's videos.
Yep. Now what I'll do is I'll switch to the other one quickly.
Whoa.
This talks about the fact there are numerous options for diagnostics, and one of the things about diagnostics is you want to choose the technique which is most suitable. So why would you choose, for example, X-ray? Well, also, A, cheap, B, quick. No? It's very accurate for non-invasive. So that is a really effective use for X-ray. But you're not going to use X-ray on that one. Well, there is a bone. I can see it. It's right around there. That's a skull. You're not going to pound the brain with X-rays.
What's the point of two-dimensional image? Because you can only see
Well, there are a number of things going on there, but the good news is, the thing is, because it's soft tissue, normal X-rays machines, which are hard X-rays, won't even pick it up, except it's maybe an amorphous blob. Whereas MRI allows you to see grey and white matter and other things, and those spots are not good news.
Right. So would they choose a CAT scan or like?
Depends what they're looking for, and depends on cost. That CAT CT scan, of course, is much cheaper than MRI. That one, by the way, can you pick out what it is? Yeah, it's intestine. It says the vertebra, backbone. It's cut down through here. Actually, I don't think this is the one I want to use. Yes. Let's see what else we've got here. This might be the one I want. Okay, which I said before, just quickly look at radioactive isotopes, which emit what sort of radiation, Marnie? Yeah, right. So you're doing diagnostic nuclear medicine, what sort of radiation you want? Gamma, correct. They're injected intravenously and inhaled, or they can be ingested too, drunk. Picked up by the gamma camera, and there are some special terms which I'm not going to go around about. There are different types of nuclear imagery, so single photon emission can computed tomography. That there for you guys is a gamma camera. That's a newer looking one. You lie down on the bed and then it moves back and forward. This is a bone scan, whole body bone scan. Now, this is important and I want to point out why. These are taken in 2 different time frames. You can see that the spine or the vertebra, which are taking up, you can see that. No, actually. That's a shield so that the person doesn't become sterilised by the... what you can see here, see that there and that there? They're the kidneys showing up, so they're filtering, it's already starting to filter out the medicine. But you'll notice something, there's a skull. Yes. That thing there is a bit of a concern. It could, it actually could, it's a source of high uptake of the nuclear isotope. It could possibly be a start of a bone tumour going in through the back of the skull there. So that's bad news. They need to further investigate that one. They have pictures of the lungs here. And what you've got is various pictures of the digestive system running there. Now this is actually interesting because this is a double scanner. This is CT and PET, and I won't PET. Do you want us to go on to PET?
So we haven't actually done it.
Haven't done PET yet. I should be doing endoscopes. Got to do PET first, and I can do endoscopes with you. PET scanning is used for oncology, which is cancer, for function of organs, for metabolism, and so on. PET is simply the positron emission tomography. All right. Now it's a nuclear medicine because it involves the use of radiation. Now the thing is, it's images of emitted. It's not actually images of emitted positrons, but it uses positrons to make it work. So they have what's called positron emission taking place. Now I'm better off showing you that on the other. Okay. So what happens essentially is they, again, inject you with a source on a pharmaceutical. It goes into the body where you want to do, and it reacts with the body. They use a detector to see what's going on. It's looking for gamma ray, and the gamma ray emission is at 311 kilo electron volts. It's always 311? No, 318, I think. I'll look it up, it's in there. But it's always a specific type. And the thing is, it's in pairs, and there's a reason for that. A positron is the antimatter version of an electron. It's an electron with a positive charge on it. And when an antimatter meets matter, what happens? It annihilates, it cancels out. And when it annihilates, it turns itself to pure energy. And in this case, where a positron meets an electron, it creates 2 gamma rays at exactly 180 degrees to each other at 311 kilo electron volts, which is a known frequency. Might be 380, I'll have to look it up. The way it happens is because of nuclear decay. As you know, in all atoms, you have a central area, which is the nucleus, surrounded by electrons, which may be particles of cloud light or waves, depending on how you look at them, you know, the dual particle light. Now, why neutron's different colour in there? The reason is because... Yeah, the reason is because positron decay only occurs in nuclei where there's an excess of neutrons. Okay, so there are particular things. Positron decay only occurs in atoms with an excess of neutrons.
How can you have an excess neutrons in the neutral? Like, I don't understand.
There's too many of them in there. It makes it unstable. Now, the thing they're saying here is fluorine-18 is a positron emitter, and it's linked here with FDG, which is a type of glucose which is taken up by the brain.
So we've just been introduced to this positron.
Yep. Sorry, not neutron excessive, neutron deficient. I'll get it the right way around. So where there's too few, where there's only there's not enough of them.
But what does that mean? When there's not enough?
Well, what it means is that if you have a very massive atom with a very large number of particles in the nucleus, for the energy to be correctly distributed, there has to be a certain number of protons versus neutrons, right? In this case, there is an excess of protons compared to neutrons. So there's a lot of protons there for that size atom. Yep.
So if you're saying neutron deficient, you could say there's too many protons.
Yeah.
What's the anti-neutrino?
Okay. So what you get when it breaks down is you have a positron given off, the positive electron, right? And you have some energy given off it in the form of a neutrino is a type of particle. It's a very small subatomic particle, which is highly energetic. And no, it's not, because its mass is the same mass as an electron. Its size is the same size as an electron. It's exactly like an electron, except it's got the wrong charge. Now, so what it does is it produces the antineutrino, which they used to think was massless and only travel at the speed of light. It does travel at high speed, but it isn't quite massless. Creates a positron, which is ejected, and it leaves behind a neutron in the nucleus. So a proton is changed into a neutron by the release of an antineutrino and a positron. That's PET emission. Or
So sort of like in the proton is an antineutrino and a positron.
no. The proton itself is made of quarks, and the quarks rearrange themselves to make a neutron, a neutrino, and a positron. 511, I was right. So, when you get the emission of the positron, when it hits a nearby electron, it then decays, or is annihilated, and gives off the gamma beam. And so, if you've got where these things will only travel very short distances before they will hit an electron, probably, and you'll end up with the emission of a gamma ray. Now, the beautiful part of this is because there's two of them given out at the right energy. One, you can look for that energy. Only detect gamma rays that energy, so you don't have to worry about background radiation and all the other stuff going on, or stray nuclear isotopes and previous diagnostics. And because if it was there, how long will it take for that one to arrive compared to that one?
That one will be shorter.
Yeah.
You can pinpoint it really easily.
Pinpoint where it came
You've got,
from.
like, the line that it's on. You've also got the two different times.
Exactly.
But maybe like the person you would want to align with pretty well on the machine.
They do. The machine is well aligned.
Right, so the gamma ray is injected
No, not the gamma ray. The person's injected with a positron emitter in a pharmaceutical, which carries it to the part of the body. Then it gives off the positrons, which hit electrons inside your body. They're annihilated. And so they give off two gamma rays at 511 kilovolts, which go at exactly opposite each other. And you have a detector around you.
So in other words, the gamma ray detector, but it's called a positron
Emission tomography. Yep.
Wouldn't it hit an electron before it reached the brain if you transfer the brain?
Well, what you need it to do is give it enough time, because it doesn't happen instantaneously. It happens over time, because like every radioactive element, it decays at a constant rate. So if you want to go to the brain, you give it that FDG, that type of glucose. It will get carried to the brain. You give it a bit of time to accumulate there, and then you start your scanning. And so the positrons coming off that stuff will hit the electrons in the brain. They'll be annihilated. You give off the gamma rays, and you can measure, because you've got two.
How come the gamma rays won't go like that? One up, one down. How come they go
Well, it's
perpendicular to your body?
well, they don't always,
Yeah.
but enough of them go in the right plane to be picked up.
So some could go like up that way. down
Yeah,
that way.
but it's always 180 degrees to each other, which is neat, because then you know what the
So
source is.
the detector only picks up the ones that are
in that plane. That's right. And as it says, you can get spatial resolution because you can work out by the distance it is from timing between the two measures how far they are, and that gives you a way of making an image. Now, there are questions about noise and whatnot, but what you can see is this is a pattern from the brain. This goes way beyond what we need to have. Now, you notice something about how it works? That's the camera or the detector. What does it look like? It's exactly the same. Exactly the same construction, except it's just a gamma camera. Don't need to worry about any of these things here.
How many times did you do something like this before it started affecting cat?
How many times can you do it? Well, what do I want to look at? Well, that's the one we just looked at, isn't it? Yep. Off the top of my head, I'm actually not 100% certain, to be honest. Oh yes, there is definitely a limit. I'll come back to this afternoon.